Alright, welcome back everybody. Today we are going to be looking at logarithmic and exponential equations. When we start this, our first objective is going to be that we can solve logarithmic equations. And we remember that solve just means we're going to find the values of the variable that they make these equations true. Okay, that's been one of our dominant directions in all of our algebra studies, to solve. Before we do any problems, I want to give you a quick hint. In order to avoid extraneous solutions with logarithmic equations, find the domain of the variable first. Remember that the argument of a logarithm needs to be positive, and so we only want to find solutions that lead us to a positive argument. Any other solutions are extraneous. Jumping right into the solving today, example problem number 1 from our textbook, the Sullivan and Sullivan Precalculus, wants us to solve the equation 2 times log base 5 of x is equal to log base 5 of 9. So according to my hint, the first thing I should do is find the domain of my variable. And in this instance, my variable is the argument, and I know the argument has to be positive. So I'm only going to find solutions to this equation that are greater than 0. Looking at my equation, I see 2 equal logarithms, but the left-hand logarithm is multiplied by 2. So using one of our properties of logarithms, if you watched the previous video, it's the property I said to writing glitter pen and highlight and circle and put stickers on it. It's the most important property we're using right now. You can see I've rewritten that coefficient 2 as an exponent on the argument. So now I have 2 equal logarithms with equal bases. And because logarithmic functions are one-to-one, we know that if we have 2 equal logarithms with equal bases, then those logarithms have to have equal arguments. So my next step can just be to set the 2 arguments equal to one another. Obviously now we're into the land of quadratic equations. We can solve this one by taking the square root of both expressions. X is going to be equal to positive or negative 3. Now when we look at our 2 solutions, we've claimed that x is equal to positive 3 or negative 3. Remembering our domain above, x cannot equal negative 3 because x has to be greater than 0. So that solution is extraneous. I'll cross out that equal sign. All right. Then, moving forward from there, we should check our solutions. So checking my solution by substitution into the original problem asks, is 2 times log base 5 of 3 equal to log base 5 of 9? My question mark over my equal sign. Using the property we mentioned before, I can rewrite the coefficient as an exponent on the argument, and then I can simplify that argument stating that log base 5 of 9 is equal to log base 5 of 9. Obviously that's an identity. This checks out. I can go back to my original equation I solved and highlight that solution that x is equal to 3. Pause the video here for a moment. Make sure that you have this equation and its check in your notes. Okay, the next thing I want to do for a minute is I want to get my graphing calculator, and we're going to check that solution graphically as well. So when I want to graph this, the first thing I need to do is I need to enter my 2 expressions in y1 and y2. So my first expression was 2 times log base 5 of x. Well, I don't have a base 5 button on my calculator. So I'm going to use the change of base formula to rewrite that as either a common logarithm with a base of 10 or a natural logarithm with a base of e. It doesn't matter which one I choose. I have buttons for both on my calculator. So I'm going to say y equals 2 multiplied by the natural logarithm of x divided by the natural logarithm of 5. y2 was the other side of my equation, and that was a log base 5 of 9. Again, I'm going to use change base, so I'm going to say the natural logarithm of 9 divided by the natural logarithm of 5. Graphing this, there's my y1, and there's y2. Now, I can see that that second expression is just a horizontal line, which makes sense because if I look at the expression, it was constant. So that's just the graph of my constant. In order to find the solution to the equation, I need the intersection of these two graphs. So I'll go to my calculate menu, choose the intersect command. It wants a point on the first curve. If I try and press enter right away, my calculator is not going to do that because there is no defined point at x equals 0. So I'll just arrow to the right a small amount, and now I've got a point on my first curve. Then I need a point on my second curve, and then a guess. Now I know that the solution was 3 from when I solved it algebraically. I can arrow over or even type in 3. My guess isn't critical there. Here I see the intersection of these 2 points, the x-coordinate and the y-coordinate of the point they have in common. And we can see that yes, x is equal to 3. And we have verified that solution that we found algebraically using our graphing calculator. Please pause the video and make sure that you can do the same on your graphing calculator. Alright, moving along, solve some more equations here. Second example problem. Log base 5 of the quantity x plus 6 plus log base 5 of the quantity x plus 2 is equal to 1. Remember, the first thing I'm going to do is I'm going to consider the domain of my x values, my variable. There are 2 arguments to consider here. The quantity x plus 6 is only positive if x is greater than negative 6. The quantity x plus 2 is only positive if x is greater than negative 2. Because I need both of these to be positive, I need my values for x to be greater than negative 2. Obviously, any value that's greater than negative 2 is also greater than negative 6. So my domain for my solutions is my x values have to be greater than negative 2. Now I'm going to go about solving this using my properties of logarithms. First thing I'm going to do is remember that the logarithm of a product is equal to the sum of 2 logarithms with the same base. So now I'm going to rewrite this as a single logarithm, base 5, of the product where I multiply my quantity x plus 6 by my quantity x plus 2, and that's equal to 1. Now I can use my definition of logarithms to rewrite this. Remember, we defined logarithms with 2 equations, saying that if this equation is true, then this equation has to be true. Again, we're now in the land of quadratics, and we can solve this just using our algebra skills. I've used FOIL to multiply the left-hand expression. Obviously, 5 to the first is just 5. Subtracting 5 from both sides of the equation gives me a standard form quadratic. I'm going to solve this by factoring using the zero product property and then solving each of those 2 factors equal to 0. Now, why have I crossed out the equal sign on the negative 7? The reason I've crossed out that equal sign is negative 7 is not in the domain. Right? I did not show the check for my solution x equals negative 1, but you should do so and verify that negative 1 is a solution to this equation. I'd like to take a moment here to point out that it is possible for logarithmic equations to have negative solutions. Don't be thrown off just because you see a negative number. You simply can't have negative arguments, but the value negative 1 doesn't create a negative argument in either one of those logarithms. Go ahead and pause the video now and make sure you have this example completed in your notes. Alright, moving along. Gave away all the good stuff there. Example problem number 3, very similar to the one we saw previous, except now I've got a logarithmic expression on the right-hand side of the equal sign as well. I'm going to consider the domain for my variable before I get started. I know that each one of these arguments has to be greater than 0. So here, x has to be greater than 0. Here, x has to be greater than 4. And here, x has to be greater than negative 6. When I consider all 3 of those, as long as x is greater than 4, then it's obviously greater than 0 and negative 6. So the value of my variable has to be greater than 4 when I find my solution. Now I'm going to use the same property I referenced in the last problem. I know that the logarithm of a product is equal to sum of two logarithms with the same base. So I'm going to rewrite this left-hand side as the logarithm of a product. In my next step, I'm going to use the fact that logarithms are one-to-one. Since I have two equal logarithms with equal bases, they must have equal arguments. Yet again, now we're in the land of quadratic equations. I'm going to simplify that left-hand side using the distributive property. I'm going to use subtraction property of equality to write my expression standard form of the quadratic equals 0. Again, I'll solve that by factoring. Zero product property to set my factors equal to 0, and then solve each factor. So here I end up with solutions x equals 6 and x equals negative 1. So x equals negative 1 is not in the domain that we mentioned earlier, so I'm going to cross that out. X equals 6 is in my domain, and if you guys check that algebraically, you will see that it is a solution to this equation. Go ahead and pause the video now and make sure you have this example in your notes. Next thing I'd like you to do while we still have this example up is use your graphing calculator to justify this same solution graphically. It'd be a good habit as you work through these example problems and some of the practice to make sure that you're comfortable solving these graphically as well as algebraically. Since we've verified our answer algebraically, we don't need to show any writing for the graphic solution, but it's good that we can do it within our calculator. Let's move on to another example. Our next examples come with the objective that we can solve exponential equations. All right? When we solve an exponential equation, we should expect our variable to be where? In the exponent, that's right. So here's example 4. 2 raised to the x power is equal to 5. Now we've solved some equations like this already. We'll jump through this one pretty quickly. No need for me to consider the domain here, because remember the domain of an exponential is all real numbers. So all I'm going to do is rewrite this using the definition of logarithms as x equals log base 2 of 5. And that is the exact solution to this equation. If you're comfortable with that exact solution, go ahead and highlight it, and we're done. Now, if we need an approximate solution for this, we know this answer's got to be bigger than 2, because 2 squared is equal to 4. And the answer's got to be smaller than 3, because 2 to the third is equal to 8. We can approximate this using our graphing calculator. My graphing calculator doesn't have a base 2 button, so I'll need to use the change a base. I'm going to change this to a natural logarithm with a base e. So now x is equal to the natural logarithm of 5 divided by the natural logarithm of 2. And my calculator will handle that if we want to take a look at that. The natural logarithm of 5 divided by the natural logarithm of 2. And we see our solutions approximately 2 and 322 thousandths. We said our solution was going to be between 2 and 3, so that makes sense. And that's our approximate solution. Go ahead and pause the video for a moment and record this example. Okay. Now that you have that recorded in your notes, we're going to look at a second way to solve the same equation. So here's another way to solve the same thing. My equation was 2 to the x power equals 5. Because I know that I'm dealing with one-to-one functions, I can take a logarithm of each side, and in doing so I can choose any base I want. So I'm going to choose that base e again, and I'm going to take the natural logarithm of both sides. So the natural logarithm of 2 to the x power is equal to the natural logarithm of 5. I'm going to rewrite the exponent on my argument as a coefficient. We've talked about how important that property is. So now x times the natural logarithm of 2 equals the natural logarithm of 5. And to solve for x, I can divide by the factor natural log of 2, telling me x equals natural log of 5 divided by the natural log of 2. We can see that solution here and here. Obviously, if I approximate here, I'm going to get the same approximation that I did above. So there's a second way to solve that equation. Go ahead and pause the video and record that method in your notes as well. All right, cruising right along. You guys are doing a great job, I'm sure. Next equation we're going to look at is 8 times 3 to the x power is equal to 5. Now, a word of caution here. Every year, I have a student or two who gets a little bit ahead of themselves and they disregard the order of operations, and their brain just has to multiply the 8 times 3 and make this 24 to the x power. Remember, because of the order of operations, I would need to simplify 3 to the x before I did any multiplication, and so I cannot multiply 8 times 3 here. However, it's a real easy step to divide both sides of the equal sign by 8, and now I have 3 to the x power equals 5/8, which, all things considered, is going to be the same type of problem as the previous one, 2 to the x power equals 5. All right, there's really no difference. So I could solve this using either of the two methods we showed before. The easiest way is to use the definition of logarithms and rewrite this as a logarithm. X is equal to log base 3 of 5/8. There's my exact solution. If we want to approximate this, again, my calculator doesn't have a base 3 button, so I'm going to use a change of base. I've chosen the natural log, base e here. So I've got natural log of 5/8 divided by natural log of 3, and that gives me my approximate solution, negative 428 thousandths. And there we go. Go ahead and pause that video. Make sure you've got example 5 in your notes. All right. A little more challenging problem here. This will probably be the most challenging type of equation I ask you guys to solve when I assess you in this unit. What we have now is we have an unknown exponent on both sides of my equation, but I have different bases for those powers. So I have 5 raised to the power x subtract 2 equals 3 raised to the power of 3x plus 2. In this instance, the only real effective method for solving this is to take a logarithm of both sides. So I'm going to take the natural log of the left and right hand expression. After I do that, I can use that all-important property to rewrite the exponents on my arguments as coefficients. Because those exponents were binomials, I'm going to need grouping symbols here. So I've got my exponent now written as a coefficient on each logarithm. These two logarithms, natural log of 5 and natural log of 3, are just constants. So I'll use my distributive property here so I can rewrite these expressions without any parentheses. Look at how that distributive property worked. I'll give you a moment there. Now, the next step in solving this is typically the most challenging step for my students. We're trying to solve an equation for the variable x, and we have x on the left-hand side here, and we have x on the right-hand side here. So in order to solve for x, we're going to need to subtract one of our x terms from both sides of the equation to get the x's on the same side. When I do that, I'll go ahead and get my constant terms on the other side. So you'll notice I've added 2 natural log of 5 to both expressions and subtracted 3x natural log of 3. Now my left-hand expression has my 2 variable terms. I can't combine them because they're like terms, so there's only one way to write this using a single x. What would that be? I hope your answer was either distributive property or to factor out x. Those would be the same idea. So I'm going to use the distributive property to factor this x out of both terms on the left-hand side. So now I have x times this difference of logarithms equals my right-hand expression. And to solve for x, we're basically at the end of the tough stuff. We'll divide both sides by that quantity, and this is my exact solution. I know that doesn't look real pretty to some of you, but we have isolated x. We have found the value of x that makes this true. We can enter this into our graphing calculator and get an approximate solution. X is about -3 and 212 thousandths. Go ahead and pause the video here. Make sure you've got this example in your notes. You might want to take a little extra time with this one since it's more challenging. Okay, so we're back looking at this example 6. You've got it in your notes. I want to take a moment to use our graphing calculator to make sure that we can all approximate this. That's kind of a nasty expression to be approximating, so I want to make sure we can all do that. When I have two terms in my numerator here, I'm going to need to make sure that I use grouping symbols. So this grouping symbol is for my numerator. I don't know if you guys can see that. I'm going to move it over. All right. So my numerator is 2 natural log of 3. I'm going to close that parenthesis that the calculator put in for the argument, plus 2 natural log of 5. I'm going to close the parentheses that I started for the numerator, so I've grouped that entire numerator together, and now I'm going to divide it by the entire denominator. So again, I need parentheses for the entire denominator. The natural log of 5 minus 3 times the natural log of 3. Those last two parentheses there, I closed off the parentheses on the argument, and then I closed off the parenthesis that contained the denominator, and you can see that when I round to 3 decimal points, there's our answer. Make sure that you can do this on your calculator. Pause the video if you need to do that now. Okay. I want to spend a little more time talking about that solution. If you're following along in the textbook, this conversation is not in the textbook. We're just going to do it on our own. We talked about how that expression looks pretty nasty to put into our calculator. So if we chose, we could use some properties of logarithms to clean this up. Obviously, we know that we can rewrite the coefficient on a logarithm as an exponent on its argument. So I've rewritten the coefficients 2, 2, and 3 as exponents on the respective arguments. Then I can just simplify those arguments. So now I've got this. If I want to clean it up even more, I know that the logarithm of a product is equal to the sum of two logarithms with the same base. So I can rewrite this numerator as the logarithm of the product, 9 times 25. The quotient of a logarithm equals the difference of logarithms with the same base. So I could write that as the natural log of 5/27. Simplifying 9 times 25 gives me the natural log of 225. There's no reason to do anything with the rational number 5/27. So I can show you using properties of logarithms that this and this are equivalent. Obviously this is a little bit cleaner. If we wanted to see that on our graphing calculator, we could evaluate natural log of 225 is divided by the natural log of 5/27, and we can see we have the same approximate solution either way there. There you can see the whole thing at once on the screen for the graphing calculator and written here algebraically. That's just an opportunity for you to see that we could clean that solution from the previous problem up a little bit. This is not necessary work. We were fine with the solution like this. We had the variable equal to a constant, but this is just a little bit prettier for some people. All right. Pause the video if you want to get that in your notes. That's kind of up to you. All right. Next example looks pretty wild here. 4 to the x power, subtract 2 to the x power, subtract 12 equals 0. Now, I'm going to show you this example, and if we were having regular class right now, we would do a few of these and I'd have you practice them. I'd put this on your assessment, but given the circumstances we're working under right now, this is probably one that I'm just going to show you here, but not have you practice and not assess you on, just due to the level of difficulty. Okay, so this is what I'm going to do with this, and this is something that I wouldn't naturally expect you to see on your own, but I'm going to rewrite that 4 in my first base as 2 squared. The reason I'm doing that is so that both of my powers have the same base. Now, I know when a power is raised to another exponent that I'm going to multiply those two exponents. So normally I would write that as 2 to the 2x. But I also know that multiplication is commutative, so if I wrote that like this, I hope you can see there's no difference between these two due to the fact, again, that multiplication is commutative. The reason I'm going to do it like that is I want you to see that this equation is quadratic in its form. The term that I have here is the square of the term that I have here. All right, that makes this quadratic in its form. In order to solve this, I'm actually going to step away from exponentials for a minute, and I'm going to use what's known as a u substitution, and I'm going to use the variable u in place of that power 2 to the x. So this and this are going to be replaced with a u. In doing so, now we're back in the world of quadratics. Okay, I realize this is a much simpler equation than the one we had a moment ago. I'm going to solve this by factoring and using the zero product property. If I was unable to factor this, I would have to use quadratic formula or completing the square. So now in this situation, I've got u equals 4 or u equals negative 3. Okay? So I have found two values for the variable u. However, I'm actually not solving for the variable u. I'm supposed to be solving for the variable x. So all of this work is with an easier variable. Okay? All I need to do, though, is substitute back in what I had said earlier, that u is equal to 2 to the x, and in doing so, this becomes 2 to the x equals 4, or 2 to the x equals negative 3. Solving these is pretty simple. I'll put it on there all at once. If 2 to the x equals 4, I can write 4 as the power 2 squared, so 2 to the x equals 2 to the second is only true if x equals 2. Over here, 2 to the x equals negative 3 has no solutions because we know 2 to the x has to be greater than 0. So there's the entire problem. I know it takes up the whole screen. I have to back this up just slightly so we can see it all. Oh, it's still tight. Our only solution there is that x is equal to 2. Okay? Go ahead and pause the video and make sure that you understand this example. But like I said, given our current distance learning, this is probably not one that I'm going to assess you on. But it's a neat problem to see with that u substitution. Okay. Last objective today. We're about done with our video. Our last objective is that we can solve logarithmic and exponential equations using a graphing utility. Now, I had asked you to make sure that you could use your graphing calculator to solve any of the equations we've looked at so far, but we did our work algebraically, so we didn't show that graphing. Sometimes we're going to be faced with equations that we have no clue how to solve algebraically. Here, I've got the variable x as a term on the left-hand side and as the exponent on a power in the same expression. and I don't have a clue how to solve this algebraically. So if I don't have a chance to solve this thing algebraically, this is a good candidate for approximating using a graphing calculator. When I solve with a graphing calculator, there are two methods we use. We use either the zero method or the intersect method. Since I have a non-zero expression on the right-hand side, I'm going to solve this with the intersect method. So here I'm going to define the two functions I'm going to enter into my graphing calculator. All right. So go ahead and grab your graphing calculator. In our y equals menu, let's clear out our earlier problem. All right. We are going to, pull that up so you can see it. We're going to graph x plus e to the x, and then we're going to graph the constant 2. We know that'll be a horizontal line. When I graph this, there's my first function, there's my second. Remember, I'm looking for the intersection point. So I'll go to my calculate menu, the intersect command. I need a point on the first curve, press enter. I need a point on the second curve, press enter. I need to make a guess. I'm pretty close right now. I'll press enter. And I can see this is about 443 thousandths as the x value. Obviously the y value of the intersection point is 2 because that second function was constant. Now since we haven't solved this algebraically, the only way we can justify our answers to readers is to take the time to graph this on our paper. So now what you see on both the paper and the calculator screen is the same thing. Okay. On my paper I've shown the y1 function, the y2 function, and I've labeled the intersection point here. That's the work that justifies my answer. All right. Then I remember that the definition of solve is to find the value of the variable that makes the equation true. So I want to make sure at the very end of this that I state here's the value of x that satisfies this given equation. All right. So looking back through today, we've used algebra to solve logarithmic equations. To do that comfortably, you're going to have to be good with your properties of logarithms. Maybe use that note card that we created last class. We've shown algebra to solve exponential equations, and now we've shown that we can solve these equations graphically as well. Thanks for listening. I hope you guys have a good time practicing solving some of these equations. Have a great day. Stay healthy.